So we just barely started talking about this last time, and so I want to do a quick review of some of the ideas that we went over. And in this set of slides, you'll see quite a bit of new notation as well. So this is just the overview of the topics, organization. Last time I was trying to explain how awesome this was because it's for processes that are nonlinear, they're stochastic, they don't have to be stationary. Like all the assumptions that we usually have to make in a lot of signal processing applications, you just don't have to make with this framework. There are things that you have to know or figure out. There's still a lot of engineering involved, a lot of judgment, but it's a very general and flexible framework. And it's used in a lot of ways that are surprising. And we'll see more and more applications as we work through the term, but I can understand some of you may have the same reservations that I do, where you're like, okay, great, it's this very general thing, but that just means I have to know more stuff. Like it's time variance, I have to know now not just what this function is, but what this function is at every time sample. And I have to know what the distribution of the noise term is, and that can change every time sample also. Now it's like, you're asking me to come up with too much stuff. I just don't know what that is. But you'll see that in a lot of cases, it's not really that hard to come up with these dynamic models, and there's some common ones that are used again and again. So don't be too afraid. It's very flexible, but you don't get overwhelmed with a plethora of choice. One thing, as I was doing a little bit of reading and looking at the references, I mentioned that this is sometimes called I call this the process model. And I mentioned that this is sometimes called the state model as well. And I found in one of the references that I was reading, one of the references I gave you, it's also sometimes called the system model. That was a word for this that I didn't use last time. You can see I'm getting a little bit better with this app. And in this other equation, as I mentioned, I think I've only ever seen it called the measurement model. Or I will usually call this the observation model. So it's usually called one of those two things. And again, you're taking an advanced graduate class in electrical and computer engineering, so we don't want to just hack something together. Ideally, we would like to come up with an optimal estimate of the state given some set of observations.
I'm not 100% on the distinction between the process and measurement model, or the boundary between them. If you had some system and you were measuring its output with an accelerometer or a DAC or something like that, you would like measurement noise in the accelerometer or the DAC, would that like thermal noise, would that be part of the system model, or would that be part of the measurement model? Or, because it might be partially due to vibrations in the system, or it might be partially due to the heat generated by the system, but it's also happening in the measure and affecting the outcome at the measurement level and not the overall state of the system.
Yeah, good. I wish you hadn't have chosen that example, because if you would have chosen a different type of measurement, I could have given you a much easier answer. So thermal noise, DAC noise in accelerometers, the sort of traditional straightforward way to integrate measurements is that all of your measurements are stuffed into your measurement vector, which means that all the effects of noise are represented by the noise here that go into the process model. And often you can lump the effects of noise together. So for example, the thermal noise and the quantization noise of the A to D converter can probably be lumped together in a single noise parameter. And because those noise effects are independent, you can kind of wave the central limit theorem flag, if you know what that is, and argue that it's reasonable then to model the noise as though it's Gaussian, which leaves you to just figure out what's its standard deviation, which would be great. But unfortunately, you used accelerometers, and accelerometers are something I know a lot about.
Intentionally, I used accelerometers. That's what I'm trying to do for my homework.
The way that you often incorporate accelerometers relates to something that actually I think Andy had asked about in an earlier lecture, where as part of your process model, you may, for example, be trying to estimate the velocity at time n. So this may be part of your state vector. And let me, for now, just pretend, to make this a little bit easier, that the accelerometers are taking measurements in the Earth frame, so you don't have to do a rotation. And I may even ignore the effect of gravity. But generally speaking, the velocity in the Earth frame can at least be approximated or well modeled, as long as the sample rate is reasonably high, is being equal to what the velocity is at time n plus whatever your sampling interval is times the acceleration over that same interval. And then maybe you've got some noise, and so we can say plus, I'll just denote this as u sub v comma n. So this is the, I'm lumping all the effects of the noise from the accelerometer or the integration error or the thermal noise or the A to D conversion, all is just a single additive noise parameter. So this might be an example of how you integrate the accelerometer, and that's actually a generalization of the model that we have here. And shoot, I did something a little unusual. I used W here, and I just noticed that I should make that correction. Usually I'll use U sub N to represent the process noise rather than W. I don't know why I did that. I'll try to update those slides. But anyways, in this case, this function actually has three things in it. It has the state. It has an external known input, which actually could be represented by W or U. It's probably going to confuse things, but I'm going to retain W now as the external input. And then you've got the so-called process noise that you can't observe, but you can maybe determine where the statistics are. So this is kind of a straightforward generalization where this is something that you also directly observe and somehow directly relates to the dynamics of the state and how they evolve over time, where we've got an example shown up here. So with accelerometers, you would probably incorporate that into your process model. Just because usually with accelerometers, what you're trying to do with them is integrate them and get velocity, and then maybe integrate velocity and get position. And that's all something that would happen in your process model rather than in your measurement model. But in most cases, the measurements would show up in this measurement vector. It was a long-winded response, but you asked kind of a complicated, you gave me a complicated example.
Which is, like if I was having my state space hat on, that'd be me trying, I have an unknown state which is position, right? So I have to include the accelerometer in the state space model and the process model.
Yeah, that's right. That's right. So any other questions before I irrevocably go on to the next slide? Okay, so I guess circling back from that example, what we're trying to figure out is how do we estimate the state given a sequence of measurements? And I represent the history of the measurements is going from 0 to some time, call it big N minus 1 for this particular example. Some of the articles that you'll be reading and maybe some of the chapters may have a convention that the first measurement starts at time 1 instead of time 0, but that's a subtlety that doesn't affect things very much. You'll also see that as you read, a lot of people prefer to use K as the independent variable rather than N. But my convention for all my slides is to use N. And also some will express this as the state at time N is equal to kind of what the state was at N minus 1 and the noise at N minus 1 and the model at N minus 1. It's equivalent, but my convention is always to represent it this way. So you'll see some variations, but the ideas are the same. And I updated the slides if some of you are working off of, none of you are working off of print, well, I guess one of you at least is working off a printed copy of the slides. So I did update this today, and the updates were small, but I made a few updates. So the things that you need to know in order to apply this framework are you need to know what your process model is, what your measurement model is. We'll talk about how to design those a little bit later in the term. You need to know what the distribution is of your process noise and what the distribution is of your measurement noise. And again, those can change over time. One of the things I added that I had left off, although it's sort of implied, is that you have to have a way of initializing this whole thing. And so usually that's represented by what the distribution is of the state at time 0 before you've seen any measurements. So this isn't dependent on the time at n-1 because we're assuming we don't know anything. We're not trying to model things for negative time. It starts at time 0. So this is the one case where we're trying to, where we need to specify at time 0 to initialize things what the distribution is of the state. I also want to mention that there's a little bit of confusion on terminology. I've introduced this idea of the probability of the state at time, I'm trying to remember how I represent this. I think I represent it as n given x of n-1. I've introduced this idea, and we'll see that again. And I've called this the prior. This other term that I just introduced, the distribution of the state at time 0, is also called the prior. And they both represent prior knowledge that you have about the state. This is just prior knowledge about the state at time 0, and this is prior knowledge about how the state changes over time. So they're both representing prior knowledge in the Bayesian framework that you're bringing to bear to estimate the state more accurately. But if you're reading some of the articles and you see this described as a prior, you will also sometimes see this described as a prior, and I'll use the word prior to describe both of those. In some ways, they're not distinct because this is kind of like the same transition probability, but at time 0, when we don't have a state at time n-1. So in some respects, they're the same, but some of the articles you'll be reading will distinguish between those two. And I don't actually know if they don't call this a prior. They may call that like a state transition probability, but I'm going to use the word prior to describe both of them. And I think it'll be clear what I mean from the context, but just wanted to introduce that to help prevent confusion. Okay, so these are the things you have to start off with, and a little bit more on notation, a couple slides on notation. We're trying to estimate the state. I just noticed the slide, this is clipped on the projector for some reason. I don't know how to fix that. Has it been that way the whole time?
Yes.
Just today? It wasn't that way last week.
Magic.
Okay, that was easy. So our goal is to estimate the state at time n, and it took me a while to understand this when I was first learning this material. But we've got a tremendous amount of data to help us estimate the state at time n. I mean, conceptually, what we're trying to do is kind of ridiculous because it seems so ambitious at first. At least if you really understand what's going on, we're trying to estimate the state at time n, and generally this is going to be a vector. And given all of the observations, from the very first observation at time 0, all the way through the most recent observation, or let's say the observation at time n plus L. I'm making a general case here. These measurements, every one of these measurements is vector valued. So you can imagine if you're taking 5 measurements and you're maybe 5,000 samples deep, so you're estimating the state at time n equals 5,000. We're saying we want to know what the posterior probability is of that state given that we've got 5,000 observations, each of which is a vector that has 5 elements. So you're up to 25,000 observations there.
Each of those has its own different probability distribution.
Yeah, it could. That's right. We usually think of that as a joint probability, but now you're talking about the marginal probability. This is only whatever the dimension of the state is, but this is conditioned on something that is huge and is growing with time. And it's easy to lose track of that, especially when you look at the recursions and you're like, oh, I don't really ever see y of 0 again, but it's actually there. And everything you're going to see, what the measurement was at time 0 has some impact on what our estimate of the state is at time n, regardless of how big n is. We never forget it.
Sorry. You just said that it's 5 times 5,000, which would suggest it's growing linearly. It's not, right? It's 5 to the 5,000. 5 to the power of 5,000, because there's 5 potential states at each of those time steps, And what you're looking at is paths through each of those nodes, basically.
What I was trying to describe was the dimension of the measurement vector being 5, not the dimension of the state vector or the number of discrete states it could take on. So if you've got 5, you've got 2 accelerometers and one of the channels is broken. So you've got 5 measurements, x, y, z, and x, y, at every time step, and your 5,000 samples into your rocket being launched. You now have a collection of really 25,000 numbers to work with.
Okay.
And one of the things I'm trying to emphasize is as we go through the math, it'll appear to disappear, but it turns out that very first measurement still has a finite impact on our estimate of the state at time n, and it should. And one of the things I'm going to do is use a very compact notation to represent the fact that we've had all these observations, from the very first one all the way through, usually the most recent one, but in general this could be n plus L, where L is any integer. So it may be based on the past, it may be based on the future, but in any case, there's a large collection of measurements there. And the notation I'm going to use, that you'll see in a lot of the articles as you start reading them as well, is I'm going to use y subscript 0 colon n. And that means the set of all measurements from the very first one all the way through to the last one. And again, every measurement could be a vector. Okay, so this little thing, these 4 characters represent a huge set of data. And I just don't want to lose track of that. This compact notation will help us a lot, because we actually have a lot of math to work through.
Just real quick, that n plus L notation, that's the case where we're trying to predict a previous, assuming we have a causal system, we're trying to predict the previous state of a system at time n, given all the data through n plus L.
Yeah,
so if L is positive, then that means we have, okay.
You may have future measurements.
Yeah, or back calculating or something like that.
That's right. Essentially, that's what it is. Yeah, very good. So our estimate at time n is going to be based on, again, some set of measurements that start at time 0 and go all the way up to time n plus L. And by far, in almost all of the different estimation frameworks or tracking algorithms, there's 2 cases that come up again and again. The simplest case is when L is equal to 0. And so you're trying to estimate the state x of n, and you're taking into account the observation at time n as well as all the previous observations. So this is the entire history of measurements, including the current measurement at the current time that you're trying to generate an estimate. I don't know why, but this is called a filtered estimate. That's the term that's used when you're trying to generate that estimate. And you'll see in a lot of books, including ours, in this case, they have kind of a funny notation to represent that. They'll say x hat of n, so you're estimating the state. The fact that you're generating an estimate is represented by that hat character on top of the x. You're trying to estimate the state, that's why x is there. You're trying to estimate it at time n, that's why there's a subscript. And this plus is used to indicate that you are accounting for the current measurement, the measurement at time n. So that this is with, that plus you can think of as I have it. It's positive, it's with the current measurement. The second most common case is doing what's called a predicted estimate. In general, you can think about predicting some number of steps into the future, but because of the way a lot of these algorithms work, you end up generating a predicted estimate even if you don't want it. It's just intrinsic to the algorithms, and so it's something that happens very, very often where we're simply predicting a single time step into the future. So this is the estimate. The hat means we're generating an estimate of the state x at time n without the current measurement. So this is the case with all the past measurements, but not the current measurement. So from time 0 up to n minus 1, but not including the current measurement. So those are the 2 most common cases. We'll see that a lot. This is called the predicted estimate, even though technically it would be a predicted estimate if L took on any negative number, but for in the literature and in the textbooks, the word predicted is reserved for this case. We're really talking about a 1-step ahead prediction. Is that okay? This is just notation so far, but those are the 2 cases. I'm going to be using a notation again that's similar to the articles that you're reading. So the notation I'm going to use, rather than this plus notation or minus notation, if you get a lecture from Dr. Wan this term, you'll probably see in his slides it uses k is the independent variable rather than n, and he uses this plus minus notation for a lot of the work he does, but I don't use it. So what I'm going to do is say the estimate of the state at time n given, and then I'll indicate up to what the most current measurement is. And this is super compact notation. I use the word vary. I was tempted to use the word extreme or something, because if we think about the example of having a measurement vector that has 5 elements, at every time step you're taking 5 measurements. You've got 5 sensors, 5 channels of accelerometers or something, and then you've got, again, 5,000 time steps, and we're evaluating the estimate of the state at time n, and we're doing, let's say, the filtered estimate. So we've got x hat of n given n with 2 symbols. If we think, oops, I'll get it. If we think of x hat of n given n, with these 2 symbols, with this given symbol, that vertical line, and n, I'm basically indicating, given that we're taking into account 25,000 measurements. So there's really a lot there, and it's easy to overlook that and think that there's not that much. But we really are trying to estimate the state at time n, given the entire history up to the current measurements when I use this notation. So given a tremendous number of measurements, we're trying to take all of that information and use that to optimally estimate what the state is at time n. So we're really accounting for a lot when we're doing that. So that's the notation I'll be using. That's the same notation you'll see in a lot of the reading that you're doing for this class. Any questions on that? Okay. Okay, so I don't want to dwell on this, but it's good to keep in mind that generally, if we're talking about all the measurements from 0 to n plus L, where we're estimating the state at time n, and we could have all the measurements from 0 all the way to n plus L, if L is 0, then we have the filtered estimates. We've got the entire past and the current measurement. If we've got L is equal to -1, then we're doing a 1-step ahead prediction. But L could take on more negative values. It could be -50, -500. You could, if it's from a continuous process, you could translate that into durations, like from what's the best prediction from 5 seconds into the future or 5 hours into the future. So it's very easy to generalize this and think about doing prediction many steps ahead, potentially. And then there's this idea of what's called smoothing, where you've got non-causal estimates, where you're actually using the future to estimate what the state is at the current time. And that's usually appropriate in engineering applications where there's 2 cases where this comes up, where you want to do smoothing, where you're actually taking into account future values. One is when you've got a recording, and now you want to generate the very best estimate of the state at time n, given the entire recording. And the recording includes measurements from the future as well as the past. And generally, you can cut the variance of your estimate in half by using the future as well as the past. It's kind of like, well, you've got twice as much information in a way. So there's often a big gain to be had in smoothing when you can do it for your application. The other case when this comes up is when you've got a lagged estimate. It's not really that you're doing where you've got future values, but you're simply waiting to get an estimate of your state. So you say, well, for my application, it's not a big deal if I'm able to estimate the state, and I've got an estimation lag of 10 milliseconds from my most recent estimate. In controls applications, it may be that the dynamics are so slow that that lag doesn't matter that much. And yet, by having a lagged estimate, you can greatly reduce the variance. I mentioned that you can cut the variance in past if you've got your entire recording, but most of that benefit comes from the first few samples in the future. And so in some applications where you can afford to have a lagged estimate, it comes at an expensive computation. But when you can afford to have a lagged estimate, your lagged estimate is generally much more accurate than the filtered estimate, and certainly more accurate than the predicted estimate. So those are the 2 cases where smoothing comes up. And I'll mention smoothing a few times as we go through this course, but our focus is going to be on the filtered estimates and we'll get the one step ahead predicted estimates along the way. Not that that's useful for most applications, but we'll just get it kind of as a byproduct.
I apologize for asking this question because I don't think it's going to help anybody else, but I'm trying to fit this in the framework of an HMM and just think of these as hidden states and as emissions, and thinking of the smoothing as sort of optimal state finding. Is that legitimate, or should I stop doing that?
Well, when you have discrete states, a lot of things change. A lot of things get a lot easier.
Sure.
And usually when you've got what you're describing, I think, is a hidden Markov model.
Yeah.
When you have a hidden Markov model in many applications, people are trying to find the most probable trajectory of states.
Right.
And in most of the continuous variable tracking applications, that's really hard to find, and people don't try to estimate it. So, so if you're thinking in that framework, you're going to continually run into differences because we're not after the most probable trajectory. It would be great to have, but it's really hard to get. It turns out computationally, it's just really hard to find. So that's one big difference. Another difference is that when you're in the hidden Markov model case, the number of values that the state can take on is compact enough that you can do the equivalent of integration. In the discrete case, it's just a sum. But that sum is finite in the hidden Markov model case. It may be a large sum, but computers are fast, and you just don't care. But in our application, where this is suddenly a continuous random variable, and especially when it's in a high-dimensional space, thinking of that as taking on discrete values, it breaks down. You run into what's called the curse of dimensionality, and you lose. You can't do the sums in the same way. So there's a lot of hazards, and if you've got a background in hidden Markov models and you're bringing that to bear to understand this, there's a lot of differences that may screw you up.
Thank you.
Any other questions so far? No? All right. If we focus on filtered estimators for the time being, there's a lot of different filtered estimators that we can consider. Certainly we could take the mean. This is by far the most common for engineering applications. You'll see a nice example today or on Thursday of where that's a bad idea. And I tried to show you some conceptual examples, not in the dynamic case, but in the static case when we were doing estimation theory. And you saw some multimodal distributions, maybe with a big mode, and it turned out that the mean was at a very improbable location. And there may be a lot of applications where that kind of mean is useless. I'll show you some examples in the context of state space tracking where that's also true. Nonetheless, it's the most common. And sometimes it can be hard to find a mode, which is what this one is doing. This is sometimes called the mean a posteriori estimate, or the map estimate. It's really nice, but depending on how you're estimating the posterior probability, it may be hard to do. You can also do a median for some applications. That makes a lot of sense, particularly when you've got sensors that sometimes are really far off, and they generate what's known as a heavy-tailed distribution. In those cases, something like a median estimator or some other type of rank estimator may have a lot of advantages and may make a lot of sense. So I just want you to have in the back of your mind, although as you read the articles, they all talk about estimating the mean. This is always the one that they have in mind, that there are good reasons to use other things sometimes. But nonetheless, more generally, if you take a step back, one of the things that I'd like you to notice is that every one of these estimators is driven by the posterior. The posterior is what we're after, whether we're using a Kalman filter or particle filter, even if we're using the Viterbi algorithm, all of it is driven by the posterior probability, and that's our goal. That's always what we're after. And a good estimate, or in some cases, the actual calculation of the posterior probability. So we're after that. And once we've got that, then you can use good judgment based on your application to decide what kind of estimator you're going to use once you've got the posterior. But the posterior is what we're after. I also want to mention that if you've got the posterior, it's also really easy to get confidence intervals or even to get a covariance possibly from this, and that can be very helpful in a lot of applications. Often when engineers are hacking together an algorithm, they maybe have a little bit of a background in signal processing, and they generate an estimator. You say, well, give me a confidence interval also. They can't even get started. And in a lot of cases, it's really hard to do. But if you've got the posterior, it's almost trivial. It's quite easy to get confidence intervals in this framework. Usually we do it just on individual states, so we might say, well, in the earlier example of estimating a velocity from an accelerometer, if you estimate the velocity to be 5 meters per second, 5 meters with a 95% confidence interval of what? Of negative 500 to 500, or negative, I forget what I said, but negative, or say 4.9 to 5.1. Heck of a difference in how you're going to use that information, depending on how much confidence you have. And so being able to get confidence intervals is huge when you can do it. And with a lot of what I'm going to be describing, you can get that.
That assumes that your priors are valid, though.
That information that I opened with, that you have to bring, the two models, and knowing what the distribution is of your noise, and knowing what the prior is for the state at time zero. All of that has to be accurate for everything else to be accurate. Yeah, it's garbage in, garbage out, of course. And I'm not, in even like hyper advanced course, I guess you could start to talk about robustness. How robust is it to the assumptions of the information you're feeding it? If you feed it a little bit of garbage, does it do okay? But that's actually beyond the scope of my knowledge. I mean, other people have looked at that. And in the book, you'll find like H infinity estimators is one way of dealing with the fact that you've got uncertainty about your model, but that's beyond what I'm going to be able to convey in this class. So we're going to focus just on the filtering problem. And for a moment, maybe just to confuse Eric, we're going to talk about two different posterior probabilities. And conceptually, these turn out to be important, but there's two posterior PDFs. And when you're talking about optimal tracking, and you say, well, my classmate took a class on state space tracking, and when they had the optimal tracking recursions, they looked different than what I had in my class. And that can be explained because there's actually two of them. There's a different set of recursions for what's called the joint posterior than there is for the marginal posterior. There's two of these. And depending on what book you look in or what article you're looking at, they may talk about both, but usually they'll just talk about one. And regardless of which one they talk about, they'll talk about it being the optimal recursions, and they'll talk about it being the posterior. But there's actually two, and they're both important and relevant. It turns out the more general and complicated one is actually has an easier recursion. So we're going to talk about both of these. The joint posterior is considering the entire state trajectory. So the posterior probability is not just for the state at time n, but it's for the entire trajectory of states from time zero all the way up to the current time n. And this is conditioned on, again, this enormous set of measurements from zero all the way up to the current time. Both of these are filtered, part of the filtering problem. So this is called the joint posterior because it's the joint probability of the states from time zero all the way up to time n. The marginal posterior is called marginal because it's only the probability of the state at time n given the entire sequence of measurements. If you've got a background in hidden Markov models, they're often talking about the joint posterior. The Viterbi algorithm is driven off the joint posterior. But in state space tracking, where you're dealing with a continuous case, you're usually dealing with a marginal. But there's two different posteriors, and one of the things I want to instill in you is the difference between these two. This is really high dimensional, and it grows with time, whereas this doesn't. Assuming the dimension of your state doesn't change with time, it could, but assuming it doesn't, then this is mapping from a fixed dimension of whatever the dimension of your state is to just the real set of numbers because it's a probability.
So is the joint posterior a more general case and the marginal can be estimated from that, or are they totally different?
I'll talk about that in just a minute. Yes and no. One of the things that we're going to be limited to through the entire term is working with Markov processes. State space models are Markov processes, so it's the title of the course is state space tracking, so this shouldn't come as a grave disappointment to any of you. This is kind of just a consequence of working with state space models, that it turns out we're working with what are known as Markov processes. A Markov process is one where the probability of the measurement at time in, given the entire history of what the states have been, is equal to the probability of that same measurement conditioned just on the most recent state. So it's a Markov process if and if this is true, and it turns out for the state space models that can be defined or represented by these equations, they are Markov processes. The way that you should think about this conceptually is that if this probability, and I'm rather than pointing to the physical screen, I'm trying to use the pointer on my iPad to make the screencast a little bit better. But if you're thinking about this probability, one way of thinking about when you condition this on stuff is it should give information, and it will generally make this distribution more peaked and less uniform. It will usually give you, having this condition on more and more stuff will generally give you more information about where y of n is located. And if you think about this as a single mode, it should usually make that mode a little bit narrower, the more stuff that you add. But Markov processes are different. Markov processes are processes where when you add more and more stuff from the past, it doesn't help. The probability of y of n, this distribution, is the same when you know what the state is for time x of n. So one way of thinking about that is x of n contains all the information about the past that you need to know to estimate y of n. If you've got x of n, there's nothing to be gained by knowing more about the past states, knowing more about what the history is of the states.
Isn't that obvious from the measurement model? Like, when I've seen that before, it's usually you're saying that it's just in terms of the process model, and you're saying that the next state can be completely determined from the previous state?
Well, instructors generally love it when their students say, "Isn't that obvious?" in a way. If it's obvious to you, that's great. But this is a property that as we go through and work through the math again and again, particle filters and everything else, Kalman filter and Sinta-Kalman filter, etc., we're going to be using this property over and over again. And so if it's not obvious to all students, then I wanted to state it explicitly if it wasn't clear simply from that equation. And it may not be clear to all of you, but this is something that we're going to be using again and again. And when you're thinking about the general class of stochastic processes or random processes, it's easy to create examples where this isn't true. Not all stochastic processes are Markov processes, but as Andy was saying, state space models, it turns out, are. And so all the state space models that we're working with will have this property. We'll be using this. This is used in deriving a lot of the algorithms we're going to be going through, including the optimal tracking that we'll be going through today. The same is true for the process model for essentially the same equation, the same reasons. So the probability of the state at time n plus 1 given the entire history, it turns out, is the same as simply conditioning this on what the state is at time n. And this is actually where part of that magic occurs, where I said, it was a little bit different the way I was representing it before, where I said we're going to be looking at the posterior of the state at time n conditioned on this entire history of measurements, tremendous amount of data. And sort of in one step, by saying Markov process, I did something kind of similar where I took something that was quite complicated. I missed my pointer. Oh man. Okay. I'm just going to give up. So we've got something that's very complicated, and we just simplified it pretty immensely. Rather than having to worry about, oh my gosh, how does the state at time 0, how does that relate to the measurement at time n? I mean, this could be thousands, millions of samples deep, and we're having to worry about what was happening at time 0. Well, it's a Markov process, so at least for this equation, we don't have to. You can't, this isn't Markov in the same way you can't apply that same, maybe I should make that explicit, that same type of equation here. It turns out this is not. equal to P of X of n given just the most recent measurement. That's not true, but these bottom two equations are true.
So this Markov process assumption is an self-imposed assumption, right? It's not just to make the computation a little bit simpler, I guess.
Well, this is a consequence of working with these state space models in the form that I've listed them here. So it falls out nicely. It's not as though we boxed ourselves in just to make the math work out. I guess you could argue the starting point is a lot of applications, a lot of engineering applications can be well modeled by random processes defined by these two equations. And so, well, those two equations, turns out, are describing a Markov process, and that has a lot of nice properties we can use. So that was more the line of reasoning, or at least the arguments that I'm making.
I'm not trying to follow the distinction between the two, the conditional probabilities. The P of y given x and P of x given y.
Okay, yeah, good.
Or what the reason why one's valid and the other's not.
It's like the difference between the PDF and the likelihood again, where you're saying, given some measurements, right, what is the likelihood that x is equal to something, right? And down there, you're actually talking about the PDF, and you're saying that this is what the probability density function of the output is.
Yeah, that's true. That's good. Another way of getting to the same conclusion is if you look at this model right here, and we're looking at, well, the probability of y of n conditioned on this entire history, but if we know x of n, and this is a random process we can't describe, we can actually figure out entirely what the PDF of y of n is. Knowing what x of n minus 1 is, or n minus anything, doesn't add any additional information, because if we know what x of n is, this only depends on x of n. So you can kind of reason it out just by studying that equation. But if you try to go the other way and say, okay, well, let me assume I know what y of n is, what do I then know about the probability of x of n? And you can't get there by the same reasoning. You can't, it's not clear that this is invertible. You couldn't write a similar equation where you've got x of n on this side, where x of n only depends on y of n, because it doesn't. X of n depends on the past, it depends on what x of n minus 1 was, it depends on this noise, it depends on this stuff over here.
Oh,
so you can't swap those.
that would imply that x is the state is a one-to-one dependent on the current measurement, which is just not at all true, because that's a really trivial system.
Well, you want to be careful about talking dependence, because we're talking about stochastic processes, and there's never really a deterministic dependence.
Yeah. But it has to, in some way, it has to be dependent on the history of previous measurements. Otherwise, it's just some simple function with some noise of the current measurement.
Yeah, that's right. When you know the current measurement, it gives you some information about the state. If you know the entire history, it does give you a lot more information about the state. I guess that's a third way of looking at it. The more you know about the sequence of measurements, the more accurately you can estimate x of n, but not so the other way. Yeah? How are we doing on it's been about an hour. You guys want a break? A lot of ideas here. All right. You guys have to remind me to... So this is a graphical illustration of what it means to have a Markov model, where it just explicitly shows the dependence of each measurement, like the measurement at time y of n, how it depends only on the process noise and on what the state was at time n. It doesn't directly depend on the state at time n minus 1, and it doesn't at all depend on what the state is going to be in the future. It does depend on the state, but only through x of n. The entire history of the trajectory all drives what the state is going to be at time n, but once you know that state, then y of n only depends on those two factors. Similarly, the state at time n only depends on what the state was at n minus 1 and what the process noise is. I think I said process noise earlier when I should have said measurement noise. But Yeah, I see. I've screwed up my notation here even worse. Where I've got W there and U there. My intention was to use U throughout, so that's another error that I need to correct when I update the slides. I hope that doesn't cause too much confusion. But in any case, the idea is was just to graphically illustrate the idea that the state x of n has all the information you need about the past. That's what it means for this to be a Markov process.
So again, what does state is a bottleneck mean?
It means that all the information about what the state's going to become and what the measurement is flows through the state at time n.
How is this different than a hidden Markov model? Sorry to.
The state is continuous.
No,
Okay, the state is
the state is continuous, but otherwise it's the same.
Well, but you're talking about discrete time steps, so the state is not continuous, right? Because it's distinct at n and n plus 1.
The state is in the reals.
Okay, so the state space.
That's the distinction.
Okay.
Yeah, that's right. Yeah, I mean, you can talk about continuous time state space processes. There's a whole theory and math for that. It's more complicated though, because you don't have these discrete time steps, and all of our processing is always in discrete time. We're always doing it with microprocessors. So that's why the whole class is in discrete time. There's an analog in continuous time, but that's the main distinction between the hidden Markov models that you're used to and the state space models we're working with in this class is what Andy said, that we're talking about real valued vectors for both the state and for the measurements. And that changes a lot. That has a huge impact, it turns out. Goris, did you have a question?
No.
Okay. Any other questions on this idea, working with Markov processes?
Yeah. So the Markov process kind of implies memorylessness, right? But in some cases where say the state transition does have a memory of say two states, we can probably increase the state vector to have two values, kind of cheating, keep the last two values in memory.
Yeah, that's true.
Okay.
That's true, but there are stochastic processes that are not memoryless, that are not Markov processes. I mean, you're right, this is more general, where you can take into account fixed lags, but I could describe random processes that are not Markov processes, so even though that is, not all processes are.
So we can't capture nonlinearities like hysteresis using a Markov model because then you have the memory of.
That's a great example. Yeah, good. Hysteresis would be a good example where it wouldn't be a Markov model.
Would state space work for that or not? This is state space tracking.
When you've got hysteresis, I'd have to think about that.
I've seen some people do it in the past where you can basically run two different common filters with two different process models, where you assume, because in the simple case where hysteresis is like a magnet or something, whereas you have just one hysteresis loop, and then you can treat it as a nonlinear problem where you have two different common filters, and whichever one seems more accurate and has a lower error, then you go with that one.
If you're really familiar with that application, you're really going to like this class, because there's a much better way to do that. That's a case where the state can take on one of two values. So it's basically a multimodal posterior. Given your observations, it can be in one of two locations. And with these particle filters, you can nicely represent that without having to do the switching and tracking of two different common filters. So it's good for that. But I haven't done a lot of work with hysteresis, so I'd have to think more about whether that still qualifies technically as a Markov process or not. I just don't know. I mean, based on what Andy just said, I'm inclined to say yes, but I initially said no, so now I just don't know. Sorry. I'd have to think about it. Good question, though. Any other questions that I can actually answer? Okay. Okay, so finally, the recursions. Our first recursion, our first algorithm, so to speak. So Bayes' theorem, of course, is going to come up again and again in this class. And now we're talking about the more general case. When we're talking about estimation theory, I was encouraging you mostly to think about x and y as scalars, as real valued, not discrete valued, as real valued scalars. And now I encourage you to think of both of these as vectors. So we've got a joint probability of those two random vectors, and with Bayes' theorem we can break this out two different ways. Is one conditional times a marginal, or another conditional times a marginal? And it's not always obvious, you know, I say, well, in our context this becomes, and then I start off with something that I seem to have pulled from thin air. And it's not that I'm going to expect any of you to like think up these proofs or these derivations. But I hope you can understand them when they're presented. I wouldn't expect any of you to have the insight to think, well, I'm going to pick the entire state trajectory from 0 to time in. I'm going to form a joint probability of that with the measurement at time in conditioned on all the past measurements. Like, I wouldn't expect you to think that up. But you should know that if we apply Bayes' theorem, that we can represent this joint probability that I made up, I sort of picked deliberately with malice aforethought, that we can write this in a couple different ways using Bayes' theorem. So once we start off with this, you say, okay, well, this exists, and once we have that, we can write this as, one way we can break that out using this first equation is as the probability of x of the entire trajectory from 0 to time in, conditioned on basically all the measurements, not only from 0 to n minus 1, but now we've added to the pile y of n as well. So now we've got the entire history up to the current measurement, conditioned on all that, multiplied by the probability of y of n given all the past measurements. So this is the marginal, this is the conditional, and this is the joint. And given our notation, we can compactly represent these two things simply as y of 0 to n. This is just a notational step in going from here to here. So this is one way of taking this joint probability and breaking it out. And you'll notice this is actually the thing we're after. This is the posterior that we're trying to get an equation for. And so we've taken a step in that direction. We now know this is somehow related to this joint probability by applying Bayes' theorem one way. Next we'll apply it the other way. So we'll split it out the other way in the next slide. I've got a copy of this equation on the next slide as well. And this takes a few more steps, and I'll explain this. Maybe I'll even zoom in and make some notes as we go through this. So if we split this out the other way, let me see if I can zoom in to, oh gosh, I didn't want to do that. I didn't, and I can, I can, I thought there was a way to zoom in without doing that, but I guess not. Okay. I didn't want to rotate it. That's going to drive me crazy.
Maybe if you use the zoom button there, zoom tool.
Oh yeah, that's a good idea. Okay, I'll do that next time. So we've got this same joint probability of the entire history of the state's entire trajectory, current measurement, and then conditioned on the past measurements. And again, applying Bayes' theorem, but applying it in the other way, we can write this as, again, the conditional, but this time I'm making it the probability of the measurement, y of n, conditioned on all the past measurements and the entire trajectory of the state. And then we've got the marginal. So what's left is the probability of the trajectory conditioned on all the past measurements. This is what we have. Now, if you look at all this stuff, we've got a huge pile of stuff that this first probability is conditioned on, but it's a Markov process. And being a Markov process, thank you, that's better. We can say, well, because it's a Markov process, we can drop it being conditioned on everything else, because if we've got x of n in that pile of stuff that we know, then it's the same as the probability of y of n just conditioned on knowing what the state is at time n. So that's because it's a Markov process. That's where that property comes in. And then this is the same probability. Oh gosh. Oh, that's inconvenient. Okay, there we go, that's better. This probability here is the entire trajectory, and I can break that notation out and say I'm gonna write that separately as the probability of the state at time n and the history of the state from 0 to time n minus 1. Again, this is really just a notational step. Oh, I keep hitting the wrong thing. Is all that is. That's just another way of representing that same probability. And when I write it that way, I can then apply Bayes' theorem to this joint probability as well. And again, I wouldn't have expected any of you to think of this, but we can do that. And if we apply Bayes' theorem in just the right way, this also becomes a product of a... Okay, I'm getting the hang of this. The product of a conditional, the state at time n, given the entire past trajectory, the entire set of all past measurements, and times this marginal of the past trajectory conditioned on all the past measurements. And so that was Bayes. I think it's apostrophe S. Was his last name Bayes?
Yeah.
Oops. Okay, so the apostrophe goes over there, I guess. And then this next step, because it's a Markov process, this middle probability that's conditioned on all the past values of the state, all the past measurements, because we've got the past value of the state in there, it's equal to the probability of x of n just given x of n minus 1. And this should start to now look familiar a little bit. If you look at some of these different terms, we actually have names for them. We call this the likelihood. It comes directly from our measurement model or observation model. This is what I'm calling the prior, and it comes directly from our process model. And this is just the previous value of our joint posterior. So we're getting a lot closer to having something that looks like a recursion. So this was one way that we broke out this joint probability. We have the same joint probability that we broke out another way using Bayes' theorem. And if we now solve for the thing we're interested in, which is right here, by setting these two equations equal, all we have to do is divide both sides by this term. Divide both sides by that term, and we get the recursion that we're after. Which is given in the bottom, and it's also given on the next slide. So, ta-da, we've got our first recursion. And it ends up, after all that math, being a relatively simple expression. This is the joint posterior. This is the same thing, but it's just simply the previous joint posterior. This is what makes it recursive. This again is the likelihood. Sorry, that's so coarse. And this is the prior. And this term on the bottom we normally think of that as just a normalizing constant. And the reason we don't pay much attention to that is because it's not a function of the state. It's only a function of the measurements. And really, the only purpose of this in some respects is to ensure this is a proper probability, that if you integrate this entire thing over the entire, it would be a high dimensional integral, a lot of integrals there, but if you integrated this whole thing over the entire trajectory of the states, that it would still integrate to 1 because it's got to be a proper probability. So it turns out, isn't very important. But the other three terms are, and because this is the previous value, this is the recursion. And this is why I answered your question earlier about how do you think about the scale of the likelihood. You can see it's being used in multiplying the previous value here and the prior. It's being used in that way. So thinking of it, 5 is 25% more than 4 is a good way of thinking about the scale of the likelihood function, even though it's not normalized to have unit area.
I had a question about that from before. We don't normalize it because it's just normalization. But if I'm focused on the maximum likelihood estimator and I just want to calculate the expectation of this at the end, don't I need the PDF in order to calculate that expectation, which implies that it's normalized?
It's going to turn out with, at least with particle filters, that we normalize. We'll end up with a very nice representation of the posterior that we can handle mathematically, and we can actually normalize it directly. So once we've got it, we can say, okay, this is what it is. We know it should have unit area. Calculate what its area is, and then divide by that to make sure it has unit area.
Okay, so
And that's why it's not going to matter ultimately.
So yeah, there's no point in doing it beforehand, or we can just do it afterwards.
You're going to be doing it afterwards anyway. So if you did it earlier, it would be redundant. Yeah, it turns out. So so this is beautiful. Like it's really nice to present this as a professor, because you're like, look at this great theoretical result. You can't beat it. This is the recursion. It gives you exactly what you want. It's got the entire trajectory, so you can do the Viterbi and think about how this is kind of like hidden Markov models. And it's got it's recursive. So once you take account of the measurement at time in for calculating this, all you have to hold on to is what your previous joint posterior is. You don't have to remember all the past measurements or all the past values of the states. It kind of comes along for the ride. It's great. So it's elegant, it's beautiful, it's theoretically solid, but it's impractical. You can't use this, it turns out, for a number of reasons. One of the biggest problems is that it's too frickin' big. It's too big a function for us to really handle. The dimension of this thing, we know what the measurements are. That's just data. So this is not a big deal. But when you're thinking about this as a function of the trajectory is growing with time. And so if your state vector is 10 dimensions, I'll pick this time, and you're on the 5,000th sample, you've got this 50,000 dimensional function that you're trying to somehow handle and represent. And practically, we can't. Computationally, we can't really deal with that. So it's impossible to handle unless we parameterize this somehow and say, well, we're going to assume it's Gaussian or a mixture of Gaussians, and then we get this whittled down to a finite set of parameters. But even then, those parameters are going to change with time, and you've still got the problem that the dimension of the thing you're trying to handle grows with time. So it's beautiful theory, and it's really elegant, and you can get through the math, and it ends up just being these 4 terms after you've gone through, cranked through all the math. But we can't use it, it turns out. So that's kind of a frustrating conclusion, but that's the truth, is that it's not practical for those reasons. We talked about there being 2 different posterior probabilities that we're interested in, and hopefully you now understand why generally we're not dealing with or handling the joint posterior that we just derived a beautiful theoretical recursion for. The marginal is usually what people are working with, because usually they only care about what's the state right now. Give me your best estimate given all the measurements I've got available, whether it's only in the past or maybe in the future, but give me the posterior of just the state at a particular time. The joint again has these problems that I mentioned. And earlier, the proposal came up of, well, isn't this really just a matter of integration? Just do the integral. This is a joint, and we know the marginal can be expressed as just integrating out everything that you don't care about. So just integrate your joint probability, and we're done. And wouldn't that be nice if we could? And mathematically, we can say, well, we are done. That's it. But this integral sort of hides the fact that we're integrating over something that, again, if we're on the 5,000th time sample and we've got a 10-dimensional state, this is a 50,000 dimensional integral. And the idea of evaluating that is just, forget it. That's not gonna happen. We don't know how to efficiently, as engineers, we don't know how to efficiently integrate 50,000 dimensional integrals. So that's the hang up. That's why, yes, theoretically you can do it. Practically, you can't.
So if we're talking about the special case of smoothing, right, the joint posterior, if we could optimize the cost function with the joint, that would give us the optimal trajectory. But with the marginal, we're basically saying what's the optimal value for the state just given the observations and previous values.
That's an excellent point, and you're exactly right. Yeah. And for those of you that didn't catch what Andy just said, we'll come back to it later. I don't want to overwhelm you. We will get to that later in the term. Any other questions? so far? Okay, hang on. Okay, marginal, the second type of optimal Bayesian recursions. So now, rather than looking at the entire history, now we're just looking at the state of time in. It's joint probability with the measurement, the current measurement and the current state vectors, conditioned on all the past measurements. Bayes' theorem, there's two different ways to break this out. First, I'm going to condition on the measurement, y of n. So we've got the probability of x of n given all of the measurements, and then we've got multiplied by the marginal, the probability of y of n given all the past measurements. And again, note that this doesn't depend on the state, so we kind of don't care about it. It ends up just being a constant. This we do care about, and using our the notation we adopted, we can write this more compactly is simply the probability of x of n given all the past observations up to and including the current observation. And this probability ends up being the thing that we're after. That is the posterior that we're trying to get to. So that's good. We know that this joint probability, applying Bayes' theorem, ends up being the thing that we're after, the marginal posterior, multiplied effectively by a constant. If we split this out the other way, again applying Bayes' theorem, this time instead of conditioning on y of n, we're going to condition on x of n. We end up with the probability of y of n conditioned on the current value of the state and all the past measurements, and multiplied by the probability of the state conditioned on all the past measurements. And again, as I mentioned earlier, we've got a Markov process. So if we happen to know what the state is at time n, then there's no additional information from any of those past measurements, and this ends up just being equal to the probability of y of n conditioned on the state, because it's a Markov process. It has that property. So that simplifies. Now we had our likelihood pop out, which is great. And then we've got this other term that ends up being a little bit troubling. But in any case, let's work with what we have so far. So we applied Bayes' theorem two different ways to this joint probability. We can set them equal to one another and solve for the posterior that we're interested in. So we basically just divide both sides by this term. And when we do that, we get the equation that's shown here. So we've got our posterior is equal to the likelihood times this thing here that I'll talk about in a minute, divided by a constant. Okay, so that's looking good so far. But and we know that we can get our likelihood from our measurement model. We know that this thing in the denominator doesn't depend on the state, so it's just a normalizing constant. It's not going to be too troubling. But we do have this other thing that turns out to be a little bit troubling, this thing right here. We don't have any Markov property we can have to simplify that. It's a little bit weird because it's the state at time n conditioned on the past measurements, not the current measurement, but the past measurements. And so that requires a little bit more treatment, a little bit more work. This thing is called the predicted marginal PDF. It's similar to the posterior, but the thing that's different is that it doesn't go up to the current measurements. It only has the past measurements. So in some respects, this is what we would it's not quite what we would predict, but if we wanted to predict one step ahead, this is the probability you'd probably want to use to do it. This would be conditioned on all the past measurements, but it's the probability of the state conditioned on all the past measurements. So this is that getting at that prediction step that I mentioned you kind of get for free. And again, I would not have expected you to have thought up that you're going to set this equal to this probability and then done math on it. But you should know, since I presented this, that it's true that if we have a joint probability of the state at time n and n minus 1, and if I integrate out the state, the n minus 1 term, that I'll end up with the same probability. This is just calculating basically a marginal probability starting with this joint. And I wouldn't have expected you to have that idea, but you should be persuaded that this equation is true. And once we've got this joint probability, rather than stopping there, we can break that out by Bayes' theorem again. So if I condition on n minus 1, then I get x of n given x of n minus 1 and all the past measurements times this marginal probability of the state at time n minus 1 given all the past measurements. And now we've got things we can handle, especially when we remember that we're working with a Markov process. And so, so this term here, conditioned on all this stuff, simplifies to being the same as conditioning just on the state at time n minus 1. And now this term should be familiar. This is our prior, and we can get it directly from our process model, usually. And this is the previous marginal posterior. So remember, we were trying to get to a recursion, and so it's kind of nice that that popped out. If we know what the marginal posterior was at the previous time sample, we've now got that. You know, that found its way into our equations and where we're headed. This integral is sometimes called the Chapman-Kolmogorov equation, but I don't know many people that call it that, but it's got a name, so I wanted to mention that. And we're getting closer now to a recursion. If we put these two together, we end up with, even though we're working with probabilities, we end up with two steps that are very common to these state space tracking algorithms. We've got a prediction step, and then we've got what sometimes is called a filter step, or sometimes is called a measurement update step. So basically, we start off, the first thing we do is ignore the fact that we've got a measurement at time n, and we kind of try to predict what x of n is going to be. We try to calculate the probability of x of n given only the past measurements by evaluating this integral. And again, just to point out the terms, this is the prior that comes from the process model. This is the previous marginal joint probability. And with that, if we can evaluate that integral, then we can get this equation and do that prediction step. Once we've got that, then we just multiply that effectively by the likelihood. And this is where our measurement at time n comes into play, is in this measurement update or this filter step. This is where we use the information that we have at y of n. And this will generally narrow the distribution or make it less uniform. We usually get more information about where the state is, and so this becomes more concentrated. Or if it was unimodal, the mode would usually become narrower with the addition of this step. So multiplying, that's another way of thinking about the likelihood, is that when you multiply it times your predicted probability, that it narrows it and gives you more information about where the state is. And then we've got this normalizing constant. So these are the Bayesian marginal recursions. And once again, beautiful, elegant, concise. It's just two equations with a few terms that hopefully you're starting to get an understanding of. But the catch, the reason that this is not a class on Bayesian optimal tracking, and then we don't just stop there, is that we've still got an integral. It's not nearly as high of dimension, but if we've got a state vector that is 10 dimensions, which is not unreasonable, there's lots of processes that have state vectors that are of dimension greater than 10, then we've got a 10-dimensional integral. And trying to evaluate that efficiently, especially if you're trying to do this in some real-time application, it turns out is hard, is really, really difficult computationally. You just can't usually keep up. So the integral is the weakness of this approach, and it's why almost no one tries to do this. It's usually impossible to evaluate analytically, so you can't do it that way either. You would have to do it numerically. There is a special case, which is when you've got a linear process model, a linear measurement model with additive Gaussian noise, then it turns out you can do this exactly, and you end up with a common filter recursion, so we'll talk about later this term. But generally, it's only tractable really in the Gaussian case. Even for other PDFs, it's really hard. And with multimodal distributions and high dimensions, forget it. Yes?
I don't think I understand the concept of linearity in a recursive model. Like, what is the, I mean, what are the linear properties of a recursive model?
Yeah, I understand. Rather than answering generally, I'm going to answer specifically. So when I say a linear model, I mean a model that is linear both in the state and in the noise. So this would be a linear process model would be one that could be expressed this way, and a linear measurement model or observation model would be one that could be expressed this way. So when I say a linear model, I mean a state space process that can be represented this way. It's still non-stationary,
Yeah.
because these matrices, the state transition matrix and the measurement matrix, can change over time, but it's now linear. At any given time, it's linear.
So if you wrote it out, you'd get a big giant polynomial, but it's linear in the sense that it's a linear function of the previous state.
I don't know about the first part of your statement, but yeah, certainly the second part's right. I don't know about the higher-order polynomial, but yes, this that's what I mean when I use the term linear as I was here. So so beautiful, few equations, great theory, but it doesn't work in practice. Usually, it doesn't work in practice. Prediction step requires an integral. The normalization technically would require an integral, but usually it's of little consequence so we don't usually have to worry about applying an integral for this term. Again, the state doesn't depend on that. And if we know what the probability is within a normalizing factor, we don't usually have to worry about that. I use m to represent the dimension of the state vector. I'm assuming it's constant. It could be time varying, but I'm assuming it's constant. And if m is 3 or greater, typically you don't want to try to evaluate it numerically. You could technically do numerical integration, but as you get into higher and higher dimensions, you end up with larger computation that scales exponentially with the number of dimensions. And so as soon as you get to 3 or higher, you're usually done. You usually don't want to try to do it. This is something that's known as the curse of dimensionality. This is just one instance of it. It comes up a lot. Basically, the story is that it's really hard to do things in high dimensions, and you have to be very clever to find ways around this curse. And particle filters are arguably a very clever way, although I'll discuss that more, and we'll see. Maybe they're not so clever. The Kalman filter, and assuming everything is Gaussian, is another way around this, but again, you could argue whether that's appropriate for your application. It may not be. It's unimodal. A unimodal representation of the posterior, and you may have applications where it's not unimodal, so that wouldn't be appropriate. But all this being said, what I think is often overlooked in the papers that you're going to be reading is the authors overlook the fact, I think, that if you're in one dimension, you can evaluate this integral numerically. It is 2016, and those papers were written in like the 2000s, but even then, evaluating a single-dimensional integral is easy, and a lot of their examples are, because it's easier to plot and show, are a state vector that's in a single dimension, and often a measurement that's in a single dimension as well. In those cases, you can do it. And it's really nice to have the optimal tracker as a benchmark. You're not going to beat this. This is optimal. This is the best you will ever do. And so if you can actually implement this, then it's a win. And in the one-dimensional cases, you can actually implement this. So I'm going to show you a one-dimensional example where we actually implement this type of tracker, and we'll see how well it does. How are we doing on time? Boy, we're getting there. A lot of theory today. Are you guys hanging in there, or are you guys spent? It's okay? Sorta? Some? Barely? It's a lot. I am recording it, so. Let me just say a little bit more. Hopefully this is review, and we'll stop after numerical integration. So there's lots of good numerical integration techniques. Go to Wikipedia. There's lots of good stuff there. They usually require that the integrals be definite. what that means for our application is that as an engineer, you have to exercise good judgment about the range over which you think the state vector can take on reasonable values for your application. If you're estimating the speed of a truck going down the freeway, it's probably reasonable to pick 0 miles per hour, assuming you're not going to track it while it's going in reverse. Maybe you need to go to -20 or something, but some number, and you know it's not going to go higher than some reasonable speed. 100 miles an hour would probably be a reasonable upper limit on the speed, just to give one example. So usually based on your application, it's easy to specify a conservative, approximate range for the integral, even if technically it's not a definite integral. You can just pick A and B to be large numbers. And all it's going to cost you is computation. So it's not that big a deal, especially if you're only working in one dimension. If you've got a one-dimension tracking problem, you probably want to use the approach we're talking about in this set of slides.
I guess another way you can think about that is that the limits of the integral and the part B prior, right?
Say it again, I'm sorry, the limits of the integral?
That A and B, the limits of your integral are another part of your prior, right? For the truck case, one of your priors is the truck goes from 0 to 255, for example, or something.
Yeah, good. That's a good point, that's right. So in this class, I'm going to have a lot of examples in a single dimension, not because these techniques are limited to a single dimension, but I can convey a lot of ideas. I can show a lot of stuff in the one-dimensional case that's very hard to visualize and talk about in a higher dimensional space. And so it's really nice to have the optimal tracker as a benchmark that we compare with. When I say, here's particle filters, they're great, they're horrible, they have these limitations, they have these strengths, but how do they compare to the best you could ever possibly do is a nice thing to have. And in this case, we've got this beautiful benchmark of the actual optimal, the true recursions for calculating what the posterior really is. So for estimating the posterior, we can now compare that estimate to the true posterior because we can compute it with numerical integration techniques, but only in low dimensions, and low is like 1 or 2. And again, I know it's late in the lecture, but this is rudimentary enough, and I think you've seen it before. When you were first studying integrals, it was probably taught to you as an integral is just a Riemann sum and a limit, where I'm probably not saying the name right, but the idea is that you take a function, I've got a function of x shown by the blue curve that has all these waves. It's probably a sum of 2 sinusoids. And you basically take fixed regions and represent it, I'm picking the midpoint is the height of these bars, and you add up the areas of these bars to approximate the integral. And as you make the widths of these bars smaller and smaller, and the limit is the width of those bars goes to 0, you end up with your integral. That was one of the ways that integrals were defined. Not a very sophisticated way, but that was, I think that was the way many of us as engineers in Calc 1 learned how an integral was defined. And we can actually use that as a way to also numerically compute an approximation of what the integral of a function is as well. So we're going to use that Riemann sum approximation to get a rough idea. Most of you have also heard of, if not implemented, the trapezoidal rule, where instead of representing each region as a bar with a fixed height, instead you've got a straight line approximation from where the function starts to where it ends. And so you've got a much better fit to the function, and this is a more accurate approximation of what the integral is. This turns out to be really easy to implement as well numerically, so it's really easy to code in. So that's the trapezoidal rule, and we can use either of those techniques, or you can get more sophisticated, use higher order polynomials. There's all sorts of ways of doing this. And there's more complexity here, so that's probably a good stopping point for today. I hope none of you feel gypped, like you didn't get enough content since we're stopping 10 minutes early. So we'll stop there for today. And I'll get the slides posted much sooner this time. Sorry for the delay.